George Gamow's 1958 exploration of the origins of the elements represents a pivotal moment in our understanding of cosmic nucleosynthesis. This work, emerging from a confluence of theoretical advances and observational data, provided a coherent framework for explaining the abundance of elements in the universe. To fully appreciate its significance, one must first examine the intellectual landscape preceding Gamow's contribution. The early 20th century witnessed a growing awareness of the universe's elemental composition. The discovery of spectral lines and their identification with specific elements provided the first clues. The prevailing model in the 1930s, rooted in the work of Arthur Eddington, suggested that stars were fueled by the fusion of hydrogen into helium. Eddington's proposal, though conceptually sound, left a critical gap. It did account for the existence of helium, but it didn't explain the genesis of heavier elements. This became the central question for cosmologists and nuclear physicists. Prior to Gamow, several key figures began to grapple with this problem. In 1939, Hans Bethe published his seminal papers on the nuclear fusion processes in stars, particularly the proton-proton chain and the carbon-nitrogen-oxygen cycle. These mechanisms provided the first detailed understanding of how stars generate their energy by converting hydrogen into helium. Bethe's insights, coupled with the experimental measurements accumulating at the time, gave a strong foundation for understanding stellar evolution. The next logical step was explaining the subsequent creation of heavier elements. Gamow himself played a critical role in this evolving narrative. In the late 1940s, Gamow, Ralph Alpher, and Hans Bethe, though Bethe's name was added to the paper to make the authorship seem more significant, proposed the alpha-beta-gamma theory. Their work, published in 1948, posited that the early universe was incredibly hot and dense. Under these extreme conditions, primordial neutrons would fuse into heavier nuclei, thus synthesizing all the elements. However, the 1948 paper struggled to account for the observed abundances of elements beyond helium. Specifically, the absence of stable nuclei with atomic masses 5, 6, and 7 presented a substantial hurdle. This mass gap posed a severe challenge to the theory. Gamow's 1958 work built on this earlier foundation, refining the cosmological model. He proposed that element formation occurred rapidly in the early universe within the first few minutes after the Big Bang. This period, characterized by extreme temperatures and densities, would allow for the rapid creation of elements. The core of Gamow's argument rested on the idea of neutron capture, when neutrons are added to existing atomic nuclei, leading to the eventual formation of heavier elements. The key here was the very rapid process of neutron capture, a key difference from stellar nucleosynthesis where elements are created over millions or billions of years. The intellectual framework in Gamow's 1958 paper made it an essential contribution to cosmology. Gamow argued that the initial composition of the universe consisted primarily of neutrons, protons, and electrons. Through a series of nuclear reactions, these particles combined to form the lighter elements, primarily helium and trace amounts of lithium and beryllium. The success of this hot Big Bang model was that it not only accounted for the abundance of helium, which had become a major observational constraint, also predicted the existence of a faint cosmic microwave background radiation, later confirmed experiment. One of the most significant aspects of Gamow's 1958 work was its emphasis on the early universe as the site of nucleosynthesis. Prior to this, many physicists believed that element formation primarily occurred within stars. Gamow's work shifted the focus, suggesting that a significant fraction of elemental abundances originated from the primordial fireball. He incorporated insights gathered from nuclear physics, astrophysics, and cosmological observations. By combining data on the abundance of elements with the known characteristics of nuclear reactions, Gamow's work provided a unified theoretical description. The immediate impact of this work was substantial. It provided a theoretical basis for experimental efforts to verify the hot Big Bang theory. Astronomers began searching for the predicted cosmic microwave background radiation. Gamow's work influenced the formulation of the steady-state model, which proposed a universe that was unchanging. This was the primary competing model at the time, which postulated a universe eternally in existence with continuous hydrogen creation, and was strongly challenged by Gamow's findings. The steady-state model provided a clear alternative, enabling a direct comparison of predictions. The subsequent use of Gamow's ideas had a profound impact on the evolution of cosmology. The discovery of the cosmic microwave background radiation in 1964 by Arno Penzias and Robert Wilson provided strong evidence supporting the hot Big Bang model. This momentous observation validated Gamow's prediction and solidified his theory, though the observation did not come from the work of Gamow himself. This, coupled with the ongoing development of nuclear reaction rates and stellar models, improved the understanding of the creation of elements. The focus shifted to include the processes occurring inside stars, confirming the general picture of a universe where the majority of hydrogen and helium were formed in the early universe, alongside contributions from stellar nucleosynthesis. Gamow's work, however, was subject to scrutiny. The initial model did not fully account for the observed distribution of all the elements. He could not fully explain the creation of elements much heavier than those formed in the early universe. This spurred on significant research. Fred Hoyle, Margaret Burbidge, Geoffrey Burbidge, and William Fowler developed the theory of stellar nucleosynthesis, published in 1957. This paper, often referred to as B²FH, meticulously detailed the complex processes occurring within stars that create elements heavier than helium. This included the triple alpha process, which converts helium into carbon, and subsequent nuclear reactions that formed the full spectrum of elements up to. Despite its limitations, Gamow's 1958 work provided a critical step forward. It introduced concepts that have been incorporated into our accepted understanding of nucleosynthesis. Gamow's work highlighted the importance of considering both early universe conditions and stellar processes in forming elements. Gamow's work also shaped the work of other thinkers. For example, Gamow's emphasis on the early universe as a site of nucleosynthesis influenced later models. Contemporary research on cosmological nucleosynthesis continues to refine the predictions of the Big Bang model, including detailed simulations of the early universe and nuclear reaction networks. Gamow's 1958 paper remains a cornerstone in the history of cosmology. His conceptual framework and the subsequent developments have fundamentally altered our understanding. He showed how the universe, in its infancy, laid the foundation for all the matter we observe today. Gamow's insights into the origin of the elements underscore the interconnectedness of nuclear physics. Gamow's work continues to inspire and inform research in cosmology. His contributions laid the foundation for a deeper and more comprehensive understanding of the universe's origins and evolution. The work of Gamow serves as a testament to the power of scientific inquiry and the enduring quest to understand the cosmos.